Welcome students to the next session. Let us talk the concept of mass defect. Defect means what? Less, more, but not accurate value. Okay. Now let us say you have a मैं कोई डब्बा लेता हूँ, ठीक है. डब्बे का मास इग्नोर करो. डब्बे में मार्बल्स. I keep marbles. How many marbles I have shown? 8 marbles. Each marble mass is, let us say, 1 gram. Alright? Let us say. Now, अगर मैं डब्बे का मास इग्नोर करो, ignore the mass of this container. If I weigh it, I should get 8 grams. Alright? Now let us say suppose I get 7.9 grams if I weigh. So there is a difference. How much? 0.1 grams. This is your mass defect. Okay. Now similarly, if you take the case of nucleus. If you take the case of nucleus, this is your nucleus. Now nucleus is made up of what? Nucleons. Nucleons are nothing but neutrons plus protons. Alright. So if I try to find the mass, okay, the mass of the nucleus. See, basically nucleus is inside the atom. This is our atom. And here electrons are rotating around the nucleus. So if I try to take the mass of atom, if I try to calculate the mass of atom, theoretically, what will be the mass of atom? It is mass of electron plus mass of proton plus mass of neutron only, no? So if I add all this, I will get the mass of atom. Then I will take the actual weight. Okay, I will take the actual weight. Now this is what it's supposed to be. This is what it is when you weigh it. If there is a gap, that is mass defect. So how do I find the mass of atom? How do I find? So let us see that. Any atom is denoted by like this. So this is our atomic number and this is our atomic mass number. So if I am writing 2He4, so it has got 2 electrons plus 2 protons and how many neutrons? 4 minus 2. These many neutrons. So it is 2 neutrons. So if you consider the masses of these, I will get the mass of helium. Isn't it? Simple. So what is the mass of electron in atomic mass unit? We have seen that this is 30549 AMU. Mass of proton is 1.20727 AMU. And 1 neutron is 1.00866 AMU. Alright. So how will I get the mass of helium atom? Mass of helium atom will be equal to 2 into this. I will write MP, ME and Mn. 2 into Me plus 2 into MP plus 2 into Mn. Okay. So this is what is theoretical weight. So our mass defect is defined as this theoretical weight difference with actual weight. Actually, this is what you are measuring using some instrument. So this difference is delta M. Now why it is happening? You have to think about that. Okay, if you want to write a general expression, look here. If you want to write a general expression, now this is Z, this is A. So replace this with Z, replace this with Z, and replace this 2 with A minus Z. This is the theoretical value. This is how it should be, theoretical value, right? But actually it is slightly less. Why? We will see that. See, we were discussing about Einstein's equation E is equal to mc square. Okay, so one atomic mass unit, if it is destroyed, it produces tremendous amount of energy. I told you that energy is how much? 931.5 million electron volts. Now here you have neutrons, protons, etc. inside a nucleus. Okay, now you have discovered that there is a small mass defect. So these neutrons, protons are not individual, they are packed inside nucleus. So something must be helping them. That is, there is an energy which is called binding energy. What is binding energy? Two brothers are bonded to each other. How they are bonded to each other? Is it visible? By love and affection. A family is bonded together. How? Mutual respect, admiration, compassion, So there is a binding energy in a family. So similarly, all this is a family. There is some binding energy. So where is this binding energy coming from? By this mass defect. This mass defect multiplied by c square, you get some energy. That is the binding energy of this nucleus, which is keeping it intact. In other words, if you give this much of energy, you can separate them also. If you provide binding energy, you can break that family. You can break that nucleus family of nucleons. Alright. So this is the concept behind binding energy. Where it is coming from? It is coming from that mass defect. This mass defect will be value we will obtain in atomic mass units only. Alright. So you know that one atomic mass unit is giving this much energy. So if you know if it is some 0.01 atomic mass unit, so you can calculate. For one atomic mass, this is the energy. For 0.01, how much? You can take it, no? 1 AMU, it is 931.5. Suppose the mass defect is 0.002 AMU, how much? Simply calculate. Alright. Now, we will talk about a concept called packing fraction. What is packing fraction? So let us say the mass of the atom is m and its atomic number is A. Mass of the atom is m, its atomic mass number is A. So what is this m minus A? Which is delta m. This delta m by A is called as F, which is the packing fraction. Alright? Packing fraction is just a fraction, it's a number. So any number, either it will be less than 0, it will be greater than 0, or it will be equal to 0. This carbon isotope, you remember, 6C12. For this, the packing fraction is equal to 0. Packing fraction is equal to 0 for this atom. So sometimes it can be a negative value, sometimes it can be a positive value. So this packing fraction gives us an idea about stability of nucleus. This is one of the ways of understanding the stability of nucleus. Okay, if packing fraction is negative, the nucleus is supposed to be more stable. If it is positive, it is supposed to be unstable. Okay, if packing fraction is negative, the nucleus is considered to be more stable. If packing fraction is positive value, it is considered to be unstable. So if you look at your periodic table, we have three categories. If you take the A value between 0 to 20, greater than 180 and 20 to 180. In these three categories we will study. So these are lighter nucleus, these are more heavier nucleus, this is intermediate. Alright, these heavier nucleus are unstable, and here also the packing fraction value will be greater than 0. These light nucleus are also unstable. Here also it is observed that packing fraction is greater than 0. In this middle portion, you see that packing fraction is less than 0. They are more stable. It is more difficult to break them. Okay, but these, they break themselves. Heavier, these are big nucleus, these are small nucleus. All right, so they try to break down and convert into more stabler versions. Imagine a family, if the bond is not proper, what will happen in the family? The family will try to break down. Same happens with the nucleus also. Okay, so the packing fraction number gives you an idea about how stable the nucleus is. Okay, now we were talking about our binding energy. Now suppose this binding energy I divide by A. Now this is average binding energy. This is average binding energy, and it is given by delta M by A into 931.5, the answer in million electron volts. Okay, what is this? Average binding energy. So this is also a parameter to understand the stability of a nucleus. Why we are studying all this means we want to understand whether the nucleus is stable or not. Okay, you know, in nuclear physics, using the concepts of nuclear physics, we can produce tremendous amount of energy. So which type of nucleus you will try to choose? Something which can be easily breakable or which is unbreakable. Okay, so this average binding energy also gives us an idea about the stability of the nucleus. Alright. So when we want to understand this stability of a nucleus, there is another way of understanding that, that is in terms of binding energy curve. So this is a graph that has been plotted for the elements in the periodic table. X-axis is atomic number and y-axis is average binding energy. Now why we are taking average binding energy means basically you are trying to normalize it. You know, one atom will have 20 nucleons, another will have 40, another will have 60. You know, so how to compare them? For comparing them, you are dividing by the average, you are dividing by the atomic number. Alright, like iron will have 56, let us say. So, and helium will have 4. So, because we can compare two similar things, so we are finding the average. If I ask how many marks in the class means, you will tell me the average marks. If you say 90% means most of the students are doing exceptionally well. If you say 40% means most of the people are in the failed category. So that average will give me a better idea. So here this binding energy for average binding energy is plotted, and you can see here that what happens is, so these atomic numbers from 0 to 20, 30, these are all lighter nucleus, So the lowest value is 1.11 million electron volts. It is for deuteron. Alright. So what happens is these values gradually increase, and you can see that in this region, that is below 50, you can see that there is a maxima minima kind of trend is happening. It is rising, it is falling, rising, falling, like that. And towards somewhere middle of this, at iron 56, okay, at iron 56 value, you are getting a maximum value of 8.7 million electron volts, and from there the trend is downwards. It is falling. Here it is slightly rising, it is falling here. So this central region, they provide elements of greater stability. Why? Because they have higher average binding energy. They are in the range of 7.6 million electron volts to 8.7 million electron volts. So what is the meaning of this? This much amount of high energy has to be provided to break them. Suppose I tell you, I need 10 joules of energy, I need 1000 joules of energy. For a particular atom, 10 joules of energy is sufficient to break. For some another atom, 1000 joules of energy is required. Which is more stable? Here more energy is required to break. So this is more stable. यहाँ कम energy से ही break हो जाएगा. This is less stable, isn't it? So the lighter nucleus and the heavier nucleus come under that category. They are easy to break, but the stable are very difficult to break, and iron has the maximum value of 8.7 million electron volts. Alright, in this region you see that there is a maxima minima happening. This maxima is observed for even number of nucleons. Like you see helium, you can see carbon, you can see oxygen, and sometimes if it is a multiple of 4, it is even more good. And these minima values are observed for odd number of nucleons. For example, lithium, nitrogen. You can see that there is a drop and rise in this particular region. However, this is not maximum. This value is still less than the 8.7 million electron volts. So when you move towards 50, 60 atomic numbers, there you find iron, which has got the maximum binding energy, average binding energy. So it is very difficult to break iron. Okay, iron, very difficult to break iron means you can take a hammer and break it. That is not breaking. We are talking at nuclear level. Okay, we are not trying to take a hammer and trying to break it. We are not talking about that type of breaking. We are talking at nuclear level. If you want to break, that much high amount of energy has to be given to separate an iron atom. Iron atom will be consisting of its own neutrons, protons, electrons. So you need that much amount of high energy to break it. Alright? So this is the concept behind binding energy curve. So schematically, if you try to see this curve, the curve was something like this. There is maximum minima happening here. Here it is rising, here it is drop. It is in this direction energy values. Here it is in the rising trend. Alright, now tell me, here lighter nucleus are there. Alright, suppose 2 hydrogen atoms, can they combine to form a higher, see, 1H1 and 1H2 and 1H2. So these two can combine and create 2He4. Is it possible? The answer is yes, because these are unstable and they can combine together to form an atom of different configuration. So here what is happening, that the smaller nucleus, these smaller 2 nucleus are combining to form a larger nucleus. Now this process is called fusion. So fusion is observed in this region. In this region you talk about the fusion concept. Okay, here what is happening, already the nucleus is very big. This brick will try to break up into smaller values. These are more stable. These are more stable. This is already unstable. So here what is happening? It is trying to break down into smaller versions of stable atoms. So this is the process of fission. So after 220, you can say atomic number. These are highly unstable. Okay. So little bit of energy, they will try to break off. Here, they are trying to combine to form. See, anybody wants to be stable, isn't it? You are studying so hard. Why? You want to settle down in life. You want to have a stable career. You don't want to have an unstable thing, right? So similarly here also, these unstable things try to combine and form more stable versions. The central portion is already stable. They don't require any special stability. But these unstable people, they try to become stable. So here they become stable by combining. Here they become stable by breaking off. Breaking off process is called fission. Combining process is called fusion. Now here there is a tremendous energy interface happens. Alright. So in this process actually a lot of energy is released. Combining stable means we cannot take a Fevikwik and combine them, right? Some process happens, that happens in a reactor, like a nuclear fission reactor, like a nuclear fusion reactor. So there is a big process involved in that. So it releases a lot of energy, and that energy mankind can use for generation of electricity, for many other things. Okay, and it produces tremendous amount of energy. Remember, one atomic mass unit is giving you 932 million electron volts, and it is only one atomic mass unit. Imagine for 1 gram, how much energy can be produced. So this is the whole concept behind this, why fusion happens, why fission happens, and how binding energy is involved in that. So this is about it. So in the next class we will see some more concepts. Okay then, any doubts you shoot me, I will try to answer them. Okay, till then, take care, bye bye.